It's my understanding that quantum computers would be best applied to answering the questions that have multiple factors. It's not a sort of yes, no binary question. It's a question that just has, so many influences, whether that's a question about weather or what's happening in our brains or cancer or vaccines, just things that have so many parts to it, essentially. Is that a fair assumption?
Well, there's elements there that are really important to pull out about quantum. And the way I usually describe it to my kids when they say, "Well, what is this?" I said, "Well, imagine I gave you a coin, and I didn't tell you anything about the coin. If you were to sit there and start flipping the coin, pretty soon you'd detect the pattern, right? Well, if I flip this coin 100 times, maybe it comes up heads 50 times and tails 50 times. Okay, well then I know how this coin behaves. Even if it flipped up and it was 10 times heads and 90 times tails, okay, well, you didn't give me a fair coin, but at least I know about it. Now imagine that coin was a magic coin, and you could change that probability by telling the coin, whispering the coin. Remember the magic 8 ball? You'd shake up this thing, and then a little cube would bubble out of the blue, and it would give you the answer to your questions, like yes, no, maybe, all those things. Well, imagine it's kind of like that. So I can influence this coin, and now in the end, though, when I flip it, I always get an answer, heads or tails. I only get one bit, and that's one thing to remember when we're talking about qubits and their ability to hold massive amounts of information in how they interact with each other. In the end, when I'm done, every qubit only gives me one head or tail, yes or no binary answer. So if I have 50 qubits, people say, well, that can store 50 petabits of information. It's like, yeah, if I was to record all the nuances, all the back and forth of this complex quantum system, it would take a tremendous amount of information to represent that in a conventional computer. But in the end, when I'm done, all I have is 50 yes or no's. Now, even one yes or no can be incredibly important. Should I get married? Should I make this investment? Yes or no? And so, yeah, if you ask the right question, yes or no is an incredibly powerful answer. But it's all in how you create that question. So back to our magic coins. Now imagine I had these magic coins, and in addition to me being able to influence them, they could all influence each other. And so if I had a pile of these magic coins and I begin to describe my problem to them, I'm influencing them, they're influencing each other, and they're all changing their probabilities. And that's when we say we have a quantum system that is coherent, that I've created this, and they're all influencing each other. And that's really the way in which we create quantum computing. Is we create a problem in which we describe the problem to the quantum computer. All of those back and forth influencing each other settles all those individual probabilities. And then in the end, I measure them all. I do my final measurement, and heads or tails, yes or no, every qubit then settles into one value or the other. And then I look at those, and that's the output of my quantum computing experiment. Now we have to be careful though, because just like a real coin, even if it's 99 to 1 heads to tails, that it's going to flip. I'm going to flip it 99 times out of 100. It's going to be heads, and one time out of 100 is going to be tails. I can still flip it on any one flip. It could still end up tails. So there is that probabilistic nature, and that's why often when we use quantum computing, we get the answer, and if we're lucky, our problem is something like factoring in a number. It's very hard to factor a number. It's very easy and cheap to multiply factors together and see, did you get the right answer? So that checking of it. Now, if we're saying I'm going to use my quantum computer to figure out the best way to send my fleet of trucks out, well, I actually can't check that answer. So what I might do is run it a couple times. I might say, okay, well, what is the average answer? And then I'll get that. So that's the other thing to think about these quantum computing systems. Yes, if you're lucky, if you're really lucky, then you can describe a problem with very little information, the quantum system interacting, interfering, adjusting all of those probability odds does all of the real work, and then you measure the results at the end, and then you get your yes/no answers out. Now, part of the challenge we have with quantum is we don't really know for a lot of these problems exactly how much information we have to provide in order to create the quantum computing program, but our quotes obviously program, because really we're talking about a physics experiment. We don't really know exactly how much information we have to put in. I don't know the last time you tried to upload a big file to the cloud. It might take days, right? I'm backing up some home systems right now, and I'm about 4 days into backing up a couple hundred gigabytes of data. If these quantum systems could represent not just gigabytes, petabytes, exabytes of data, well, we actually have to then move exabytes of data into the quantum system and hope that that it comes up with the right answer. So part of understanding when quantum will have an advantage is understanding, for the kind of problem I want to do, how much time and energy does it take to set up the quantum system, to run the quantum experiment, to get the answer back, and then potentially do it more than once in order to have confidence in the answer. And so all of these make quantum just so different than we think about computing and classical computing. In classical computing, I have a disk drive. I can store my program off. I have designed it with error correction, so chances are it's always going to come up with the exact same answer. We just have that model. Well, if I run it through the computer twice, of course I'm going to get the same answer unless something breaks, unless there's a fault. And the engineers have already designed it so that it'll tell me if there was a fault, and it'll check things, and we'll have error correction codes and all these things. All this is new for quantum, and even if it all works the way it was intended, that probabilistic nature means that we'll always have to check the results. We'll always have to understand, I know you gave me this answer. Now I have to figure out, is it right, or was I unlucky? We used to don't think about luck factoring into a calculation that we do, but now, because of this probabilistic nature, which is part of the reason it works at all, we have to accept that this is different. So back to the question of when we need to understand, you and I, the citizens, need to understand this. We might have to dust off not just our normal computing and mathematics, but I don't know if you took probability and statistics in school, but not everyone does. And if this now becomes a fundamental piece of understanding how this kind of computing works, then that might be something we want to put on more high school curriculum, so that people really are, again, armed with the capability of understanding and participating meaningfully in a quantum technology driven economy.